Last meeting, we discussed concepts for simple stress and axial stress. So for today, we'll have examples. Let's start with example number 1. The bar ABCD in the figure consists of 3 cylindrical steel segments with different lengths and cross-sectional areas. Axial loads are applied as shown. Calculate the normal stress in each segment. So first, let's analyze this problem. We're given this setup, and we want to get the normal stress in each segment given the following loads. So 4,000, 9,000, 2,000, 7,000. To solve for this, recall what we did for method of sections and method of joints. So for method of sections and joints, we got the internal forces of each member. So same thing here. We have to get the internal force of each segment and then use the equation for stresses in order to calculate the normal stress, which is sigma equals P over A. So the first goal here is to get internal forces P. Once again, by using method of sections, which is cut isolating the left or right hand side. So let's do that. So example number 1. Once again, we cut the segment to get its internal force, and then you isolate either the left and right side. It's up to you. Usually, you want to isolate the easier portion. So let's start with AB. Okay. So AB, the guides for where to cut are already given. So I'm going to cut here, and then obviously, the left side is much easier than the right side. So I'm going to cut, isolate left side. So let's make a simple drawing representing that. So that's your cut. And don't forget to include all of the applied forces included in that side. So we have 4,000 here. So include that. 4,000 pounds. And then wherever you cut, there will be internal forces. Okay. So there's going to be an internal force here. Now, similar to your method of sections, you can either randomly guess or make an intelligent assumption of the direction of your internal force. Now remember, all of our systems should be in equilibrium. So this should be in equilibrium. I have a force to the left. So to balance that out, I need another force to the right. And that is your internal force. And let's call that PAB. So internal force for AB. And that's your free body diagram for segment AB. Now let's do the same for the rest of these segments. Let's now move on to BC. Okay, again, cutting here, and then you can isolate either the left or right side, up to you. I'm going to isolate the left side. So once again, let's make a basic drawing of that. And then we have your smaller segment over here. Okay. And then don't forget, once again, applied loads. I have a 4,000 here on the leftmost side. And then there's 9,000 here on this side. So include that. 9,000 pounds. And once again, you have your internal force on where you cut. So you can make an intelligent guess. I have 9,000 to the right, 4,000 to the left. The force on the right is greater. So that means I need another force to the left to balance everything out. So I'm going to assume to the left. And let's call that PBC. And then finally, let's do it for CD. So this should be D. So cutting here and then isolate either left or right. Now, obviously, the easier one is the right side. Let's do that. Isolating right. And then again, don't forget your applied force when isolating the right side, right? We have 7,000. So 7,000 pounds. And then your internal force, I have a force to the left. So my internal force should be to the right to balance that. And then we'll call that PCD. And that's your free body diagrams. Next step is to create your equilibrium equations to figure out the values of these internal forces. So since all of our forces are horizontal, we'll use summation of forces x equals 0. And at start, sign convention applies. To the left is negative, to the right is positive. 4,000 to the left, so this is negative 4,000. PAB to the right, so positive PAB, equals 0. Solving for PAB, you get 4,000. Okay? Positive, therefore correct assumption. So let's write the unit, which is pounds. And then our force is away from the segment. So similar to your method of joints and sections, when force is away, that is tension. Okay, so include that there, so it's in tension. Let's do the same for the rest of the segment. So now we have summation of forces X for BC equals 0. 4,000 to the left, so negative 4,000. 9,000 to the right, so positive 9,000. PBC to the left, negative PBC equals 0. Solving for PBC, that's just 9,000 minus 4,000, which is 5,000. Positive, therefore correct assumption. PBC is towards the section, therefore that's compression. And finally for CD, okay, PCD to the right, so positive PCD, 7,000 to the left, negative 7,000. Equals 0, solving for PCD, that's just 7,000 pounds, positive, correct assumption. It's towards my section, so that's compression. So now you have internal forces. Again, the question here is getting the normal stress. So you use that in the equation for normal stress, which is simply sigma equals P over A. Okay, so for segment AB, that's sigma AB equals PAB over cross-sectional area AB. So now it's just a matter of substituting your values. PAB is 4,000 pounds over cross-sectional area of AB. It's given in your figure. This is AB. Cross-sectional area is given 1.2 inch squared. So divide by 1.2. Please solve. What's the answer? Correct, Jan and Nicole. Vico Beltran. So 3,333.33 pounds and sorry. What's the unit of this stress? Can anybody give me? Correct, Seth and Chloe. Mac, Rohon, Marinay. Very good. It's PSI. Your force is in pounds. So pound. Area is in inch squared. So pounds per square inch, or simply PSI. So PSI. And then don't forget to include whether it's tension or compression. It's going to follow your internal force. So that's tension. Okay, let's do the same for the others. So stress BC equals PBC over ABC. PBC is 5,000. ABC given 1.8. Please solve. What's the answer? Correct, Seth and Eric. Blau and Marina. So please wait for me to ask the question before you enter your answer. So 2,777.78. And once again, that's PSI compression. Then finally, stress CD for CD, area CD. For CD, 7,000. Area CD, 1.6. Please solve. What's the answer? Correct, Marino, Sacro, and Cyrus. Tenorio, Sacro. 4375 is the answer. Unit PSI and its compression. And that's it. That's number one. Do you have any questions? Please answer in the chat. Yes, no, understood, clear, none po. Okay, great. No questions. Let's move on to the next problem. Problem number 2. So for number 2, for the truss shown in the figure, calculate the normal stress in members AC and BD. Cross-sectional area of each member is 900 millimeters squared. So again, analyze first. We have this truss. We want to get stress in AC and BD. And then we're given cross-sectional area 900. So let's write that. Cross-sectional area 900 millimeters squared. Okay. And then let's mark out the stresses that we want. We want it on AC and BD. Okay. So recall, in order to get stress on an object, I first need its internal force. So what we did in number 1, we cut isolated. Here we have a truss, and we already know how to get internal forces from your truss, right? It's either method of sections or method of joints. So let's say I want to get the internal force in AC first. What should I use, section or joints? Please answer in the chat. Method of sections or joints? Very good, Matthew and Benedict. Briones, joints. Now it's possible to do method of sections, okay, it's fine. But typically, since AC is directly connected to a support, we can use method of joints. Okay, so let's start at A. As you can see here at this joint, I have this support. So I have to solve for that support reaction first. AY. And recall, to solve for the reaction at the support, get the moment on the other support. Or other support is H. So let's take moment at H equals 0 to get AY. Now notice A is roller, H has pin supports. And recall, for rollers, there's only one reaction perpendicular to the surface. For pins, it's parallel and perpendicular. That's why here on the given, the only reaction on this roller is AY. Let's continue. So let's start with AY. Rotate AY about H. So that's clockwise, therefore positive. And then multiply by perpendicular distance to H. So that's this. And that's 4 panels at 4 meters each. So this is 4, 8, 12, 16. So total distance is 16. Next, we have this 30 kilonewton force. Rotate about H, that's counterclockwise. So negative 30. Perpendicular distance is 4, 8, 12. Next, we have this 70. Rotate about H, counterclockwise. So negative 70. Perpendicular distance 4. HY, HX both pass through H, so you can just simply ignore those forces. There's no other force involved, so equate that to 0. From this, please solve what's AY. Correct, John and Nicole. Pangonil, Beltran. It's 40. Positive, therefore correct assumption, it's upward. So 40 kilonewton. And then from that, you can draw your free body diagram. So this is your joint A. I have an upward force here. That's your AY, which is 40. And then draw the line for your members. This is your AB, force AB. And then we have this FAC. Now, once again, you can randomly guess their directions or make an intelligent assumption. I have an upward force AY here, so I need a downward force, and I'll take that from AB. So this would be downward. Now, this is to the left, so I need a force to the right, so I'll take that from AC. Now we have your free body diagram. Now recall, again, I want force in AC, okay, which is this. To get that, you could use summation of forces horizontal. Now, if I do that, though, I have two unknowns, which means I can't solve for anything yet. So I can't directly do summation of forces horizontal. So we have to go through summation of forces vertical first, or Fy. Okay? So let's begin. AY upward, therefore positive AY. FAB downward, so negative FAB. FAB is at an angle, so I need to get its slope or angle depending on what's given. We're given dimension, so you're going to get its slope. This is your force AB, which corresponds to this member. So I got to get the slope of that member. And to do that, you're going to look for a right triangle, which is this. This right triangle has a base 4. So base 4. And then, as you can see, you're also given height 3. So this is a special right triangle, 3, 4. Automatic, hypotenuse is 5. So by now, you should memorize whenever you have a right triangle with legs 3 and 4. You don't even have to solve for the hypotenuse. That's immediately 5. Okay, 3, 4 or 3, 4 is the same. Now, if you're not confident with that, you can still solve for the hypotenuse using Pythagorean theorem. Okay, so that's 3, 4, 5. Let's apply that in your free body diagram as well. So this is 3, 4, 5. So I gotta get the vertical component. So copy the side that's also vertical. So that's 3 over hypotenuse 5. Okay, there's no other force that has a vertical component, so equate to 0. Considering AY is 40, please solve what's FAB. Correct? Emmanuel and Cyrus, Rico, Tenorio. So make sure you're giving me the correct sign, okay? So that's positive 66.67. Therefore, correct assumption. It's that way. And then unit kilonewton. And then correct assumption, AB tension. Actually, I don't even need to know that yet. And we can now move on to summation of forces X equals 0. Let's start with FAB. That's to the left, so negative FAB. To get its horizontal component, copy the horizontal side. So 4 over hypotenuse 5. FAC to the right, so positive FAC. Considering AB is this, please solve what's FAC. Correct? Joffrey and Mariah. Ofreros Cabello. 53.33. Okay. Now take note. You should have stored this value when using it here so that you get the actual result, which is 53.33, not 34. Okay, and then positive, therefore correct assumption. Unit is kilonewton. And then it's away from your joint, so that's tension. Now that you have the internal force, you can now begin solving for its stress. So recall equation for stress is simply sigma equals P over A. So P, or in our case, we label that FAC over area. And then all of our areas are the same, which is 900. So now let's sub. Okay. So FAC, 53.33. Once again, please use the stored value of that. 53.33. Now take note, the unit of our force is kilonewton. For stress, the standard unit is MPa, which is Newton per millimeter squared. So let's convert kilonewton to Newton. To do that, simply multiply by 1000 or times 10 raised to 3. Okay, that's kilonewton to Newton. And over cross-sectional area, 900. From this, please solve what's stress. Correct, Christian and Marino. Sacro de nada. Okay. So it's 59.26 unit. It's not PSI, that's Newton, because this is now Newton per millimeter squared, or simply MPa. So 59.26 MPa. And don't forget to include compression or tension. It's going to follow your force. So, tension. So that's stress in AC. Now let's move on to the other part, stress in BD. This is your stress BD. Okay. Now the question is, should I use method of joints or sections? Please answer in the chat, joints or section. Correct, Burse and Ian Torrevilla Emmanuel. Okay, so you can use both. Technically, you can use both, but it's easier to use method of sections. Now, why? So I've solved for these two now. I need this. I can't go through B, joint B, because I have 1, 2, 3 unknowns. Remember the rule for method of joints, you can't solve on a joint that has 3 unknowns or more than 2 unknowns. So I have to go through C to solve for these two, and then I go to B to solve for this, which is a bit longer. Instead, I'll just use method of sections, cut here, isolate. Okay, so I'm gonna isolate this side, the left side, because that is the side where I've already solved for the reaction. You can also isolate the right side. It's up to you. But if you isolate the right side, just know that you have to solve for hx, hy first. Okay. Now again, I chose left because I already know ay. Next step is to draw your internal forces. Now again, it's present wherever there is a cut section. So we have this. Okay. So let's call that F. Force in BD, so FBD. And then here, this is your force BE. And then force CE. Now, once again, for me, for method of sections, I just like drawing everything in tension. Okay, that's just my preference. You can make intelligent guesses as well. All right, so that's your free body diagram. Now, let's solve. Again, I need stress in BD, in member BD, meaning I need to get this FBD. So can anybody tell me what equation should I use to get force in BD? So that's 3 choices, summation of forces X, forces Y, or moment equals 0. Can anybody tell me what should I use to immediately solve for BD? Correct, we should use moment. If we use forces X, that's 1, 2. 2 unknowns that has an X component. So I won't be able to solve for BD immediately. So instead you use moment. Now the question here is, moment about what point? Okay. Can anybody tell me what point? Okay, correct, Christian and Chloe. and Pauline. So Benaga, Chloe, McCoy, and Pauline. The answer is moment at E. Remember, you're not confined to your isolated section. Okay? You can use anything outside of that for your moment equation. Okay, so why E? Because as you can see at E, force BE and CE pass through that, so that means I can ignore those forces. Okay? So let's do that. Summation of moment at E equals 0. Let's start with the leftmost. So rotate AY about E, that's clockwise, therefore positive AY. Perpendicular distance, you can look at the original drawing. Distance to E, that's this, which is 8 meters, so times 8. Next, 30, rotate about E, that's counterclockwise, negative 30. Perpendicular distance to E, that's 4. Next, CE passes through E, so ignoring that. BE passes through E, so ignoring that. Lastly, BD, rotate about E, that's clockwise, so positive FBD. Perpendicular distance, so let me just extend that, and this is the perpendicular distance, which is equal to 3. So times 3. There's no other force, so equate to 0. Considering AY is 40, please solve what's FBD. Correct, Mariah? And Gwyneth. So Cavero de Guzman. Very good. Oops. Negative 66.67. What happens when I have a negative? That just means my assumption for direction is incorrect. Therefore, the answer should be, so it's the same magnitude, 66.67 unit kilonewton, but instead of my assumption tension, it's the opposite. So compression. Okay, so that is what happens when you have a negative answer. Incorrect assumption for direction. Now that I have the internal force, I can finally solve for stress, which is just F over A. Once again, store that. Store. Okay, so 66, use the stored value, okay? And again, this is in kilonewton. I want that in newton, so times 10 raised to 3 or times 1000 over area 900. From this, we solve what's stress. Correct? Christine and Eric, Ablao, Franco. It's 74.07. If you use the stored value, okay? And then unit MPa, since it's Newton per millimeter squared. And then it's compression. Okay, that's it for number 2. Do you have any questions? Please answer in the chat. No questions? Great. Let's have number 3. Number 3, the figure shows a 2-member truss supporting a block of weight W. The cross-sectional areas of the members are 800 for AB and 400 millimeters squared for AC. Determine the maximum safe value of W if the working stresses are 110 for AB and 120 MPa for AC. So once again, let's analyze. We have this cable system supporting weight W. We're given allowable stresses or working stresses and their dimensions. The question is, what maximum value of W can these two carry? Okay. So we're solving for force W. So first, let's write the given. You have your area, 800 and 400, and then stress 110, 120. Okay, let's start. Stress, okay, so area, cross-sectional area of AB equals 800 millimeters squared. And then for AC, that's 400. And then allowable working stress for AB is 110 MPa. Working stress for AC is 120 MPa. Once again, we're looking for W. Now, some of you might be tempted to solve it this way. So let's say stress AC equals force AC over area AC, right? Since it's all given, 120 equals area AC 400 over AC. And then solving for PAC over 400. And then you'll say, oh, the force that it can carry is 120 times 400, which is 48,000. And then you might have that as your answer. That's incorrect, okay? Because if you're solving for this and you're saying that this is your maximum W, that's assuming cable AC will carry this entire weight, which is not the case. Even if you solve for AB, you're going to get an answer. Again, that's going to assume cable AB is carrying the entire weight, which is, again, not happening. What's actually happening is cable AB and AC both carry W, a portion of W. So you should solve it that way. Once again, this is incorrect because neither cable is carrying the entire load. So the actual load that it can carry could be greater than this or less than. Again, it depends on how much will each cable carry. All right, so let's solve it that way. Once again, what's happening is AB and AC share the load. Now we have to know how much of that load is each cable carrying. And to solve for that, we use equilibrium equations. Okay, so let's draw its free body diagram first. So you have weight downward, which is what we're looking for, right? Okay. And then we have your cables. Remember, cables are always tension, always away. So let's call this tension AB, tension AC. And then you have this, your angle. This is 40, this is 60. So this is your free body diagram upon which we will base our equations from. So let's start with summation of forces X, or equilibrium equation. Okay. PAB to the left, so negative PAB. To get its horizontal component, that's multiplying by cosine theta. Theta is 40, so cosine 40. Remember from your statics, if the angle is given from the x-axis, horizontal component is cosine, vertical component is sine. Okay, this is horizontal, so cosine. Next, PAC to the right, so positive PAC, cosine 60. This doesn't have a horizontal force, so equate that to 0. So now I have an equation relating AB and AC. To make it more obvious, let's try manipulating that. I'm going to transpose this to the right, okay? And then let's solve for TAB. So TAB is simply PAC times cosine 60 over cosine 40. Okay, again, that's just solving for TAB, transpose to the right, divide both sides by cosine 40. Let's call this equation 1. Now, there's nothing actually to solve for there. So let's move on to the other equation. Summation of forces Y equals 0. Again, let's start with AB. Upward, therefore positive. We're looking for vertical components, so that's sine 40. TAC also upward, so positive TAC, sine 60. And then weight is downward, so minus W equals 0. And then let's call this equation 2. From these two equations, we can get how much of the weight W is each tension or cable carrying. And to do that, we just sub 1 and 2. Sub equation 1 in equation 2. Okay, so TAB is this. So we'll have TAC cosine 60 over cosine 40 multiplied by sine 40 plus PAC sine 60 minus W equals 0. So now I have an equation relating PAC to W, which is what we want. Now this is a bit complicated. Let's simplify this equation. To simplify, factor out common terms. I have PAC there, so I'll factor that out. So you'll have PAC multiplied by this, so cosine 60. I'll just bring this up, times sine 40 over cosine 40. Or simply cosine 60 times tangent 40. That's correct as well. Plus sine 60. And then I'm going to transpose W to the right, so it's going to become positive W. Hey, so now you have this equation. Now, typically what you want is your force, internal force in terms of W. So I want TAC equals something times W, okay? That's the equation that we want. I have this. So to get this, I'll just divide both sides by whatever the value of this is. So please solve. What is 1 divided by this? So what is the coefficient of W? Correct? Cyrus and Gwyneth de Guzman Tenorio. The answer is 0.78. So this is 0.78 W. Now, please don't just use 0.78. Please use the entire decimal. So store this part. Or write out the entire decimal of that. Okay, now we have the relationship of PAC and W. Now I want the relationship of PAB and W. And to do that, I'll just sum this in equation 1. Okay, so we'll have TAB equals TAC, which is this, 0.78 W times cosine 60 over cosine 40. And then from this, please solve what's the coefficient now of W? Correct, Tristan and Janelle. So De Los Reyes and Bolido. It's 0.51. 0.51 W. And once again, please store that 0.51. Okay, now I have these two equations. Now I can use my stress formulas. So let's start with AB. Stress in AB equals tension AB over cross-sectional area. Stress AB is given here. So 1110 equals TAB, which is equal to 0.51 W. Again, don't just use 0.51. Please use the entire decimal of that. And over cross-sectional area, 800. From this, please solve what's W. Correct. Janelle and Tristan. De Los Reyes. Valido. It's 17,000, 173,326.16 Newton. Okay? So that's not our answer yet. That's a possible answer. Okay? So just have that on the side. And now let's move on to stress and number AC. So that's the AC over AAC. Stress AC is 120, allowable stress. Force in AC is 0.78 W over cross-sectional area AC, which is 120, which is 400. Okay, from this, please solve. What's W? Correct? Raymond and Ubaldo. And Maria Cassandra Lafredo. Okay, if you use the entire 0.78 something something, you should get 61,707.61 Newton. And again, that's not our final answer yet. That's just a possible answer. So now the question is, what is the maximum safe value of W? We have two answers because we have two given stresses. So what should be our final answer? What is max? 173 or 61? Please, everyone, please answer in the chat so I know your understanding of what we should choose. Again, the choice is 173 or 61. Type in the chat, what should our final answer be? Okay, the answer is pretty divided. Like half of you said 173, half of you said 61. The correct answer is 61. So 61,707.61 Newton. Now to explain why, okay, this means this is the maximum load for W that your cable AB can carry. And this is the maximum load for W that AC can carry. Okay, so that means 61. Our choices are 173 kilonewton, 61 kilonewton. I just divided by 1,000 just to make the numbers shorter. So this means any load that is greater than this will cause your cord AC to fail because this is the maximum that it can handle. Same thing here. Anything greater than 173, your cord AB will fail. And of course, we don't want any part of the system to fail. So our answer should be the lesser value, okay? Because I can't use 173. That's greater than this. This will fail, okay? So in short, whenever the question is asking for maximum value of force, you're going to choose the minimum value in your answer. So 61, okay? And that's it for number 3. Do you have any questions? Please answer in the chat. Okay, no questions. Great. Let's have number 4. Number 4, the rectangular wood panel is formed by gluing together two boards along the 30-degree seam as shown in the figure. Determine the largest axial force P that can be carried safely by the panel if the working stress for wood is 1120 psi and the normal and shear stresses in the glue are limited to 700 and 450 psi respectively. Okay, so again, to analyze, we're just looking for maximum value of P that we can apply here given the following working stresses. So let's write out the given first. Okay, so we're given stress in wood, normal stress in wood. I'll label that as sigma W for wood, and that was 1,120 psi. Next, we also have normal stress for glue, so I'll call that sigma G for glue, and that was 700 psi. And then finally, we have shear stress for glue. And remember, equation for shear stress, or rather symbol for shear stress is tau. So I'll write tau sub G for shear stress in glue, which is 450 psi. Okay. Now, one trick here is the amount of allowable stresses you have is the same as the amount of equations and answers you should have. Okay? So for example, here in our previous question, we have 2 allowable stresses. And as you can see, we solve for 2 maximum forces. Okay, so your allowable stress dictates how many equations you need to make. In our case, that would be 3. 1 for wood, 2 for glue. Okay, so now let's solve. Let's start with wood. Okay. So stress, or sigma W, which is normal stress for wood, is just simply force over area. So it's the entire wood itself. The entire wood itself will carry the total load P, right? It's not going to share it with anything. It's going to take the brute force, the entire force of P. So that means I can just simply write P over 8. Okay? And now, sigma W, that's 1120 equals P, which is what we're looking for, over A. A is cross-sectional area of your object, which would be this part. So can anybody tell me what is the cross-sectional area of that? Very good, Eric and Emmanuel. So Guico Ablan. It's 4-inch squared. Why? Because this part is a rectangle. So if I draw it in 2D, this is what that looks like. A rectangle with length given 4 inches. Thickness is this, which is equal to 1 inch. Therefore, area is just base times height, or 4 times 1, so 4-inch squared. So this is simply 4. From this, please solve what's P. Correct, Burst and Joffrey. It's 4480. Unit, our stress is in PSI, area in inch squared, so nothing to convert is correct. So the resulting force is pound. Okay? Again, that's not our final answer yet. That's just a possible answer. So just put that to the side. We're done with wood. Now let's move on to glue. Okay, so glue. Again, that's P over A. Now, this is your glue, right? So therefore, what I need is not just P. I need the component of P that's perpendicular to that. Okay? So perpendicular over this area, inclined area. So you can solve it that way. You can figure out what is P perpendicular and what is the inclined area. Now, luckily for us, we already did that. We already have an equation for that, which is this. Okay, so you can just simply copy this. So normal stress on an inclined plane is P over A cosine squared theta. So we can just copy that. P over A cosine squared theta. And then let's sub in our values. That's 700 psi. P over A, once again, is just 4. Cosine squared theta, angle between cross-section and inclined plane, 30. From this, please solve what's P. Correct, Janelle and Gwyneth. Guzman Bolido. 3733.33 pounds. And once again, that's just a possible answer. And then finally, let's solve for shear stress, which we also know the equation, and that's just P over 2A sine 2 theta. Okay. Shear stress in glue given for 50. P over 2A, A is 4, sine twice the angle, 30. Okay, from this, please solve what's P. Correct. Benedict and Mariah. Samanil Cavero. Also, may humabol. Correct, Romeo. Camigla. It's 4156.92. Yes, 4156.92 pounds. Again, that's just a possible answer. And now we have three answers. The question is, what's the maximum allowed? So tell me, what is the answer? What's our final answer? Everyone answer in the chat. Is it 4480, 3733, or 4156? Again, everyone, please answer. Okay, very good. Everyone got it correct. The answer is 3,733.33 pounds. Okay, so very good. You already know when looking for maximum value of force, you choose the smallest number. Okay, and that's number 4. Do you have any questions for number 4? Please answer in the chat. No questions, great. Let's now continue to number 5. Number 5, a hollow steel tube with an inside diameter of 100 millimeter must carry a tensile load of 400. Determine the outside diameter of the tube if the stress is limited to 120 meganewton per meter squared. So basically, we have an object. We're given stress and force. The question is looking for a dimension, specifically outer diameter. Okay, so keeping that in mind, let's write the given. Inside diameter 100 millimeter. So I'll write D sub I for inside diameter. What else? Your load 400 and stress 120. 120 meganewton per meter squared, right? Now this meganewton per meter squared is the same as megapascal or just MPa. So it's the same as Newton per millimeter squared. Okay, so that's our given. Now let's solve. So let me draw what's happening for you to have a better understanding. Okay. There. So this is your tube. We're given inside diameter. Okay, so we're given this. This is 100. What we want to get is this, the outer one. Okay. This is what we want to know. For DO. And then let's draw a side view. So this is your tube. It's experiencing a tensile load of 400. And once again, this is your outer diameter as well. Okay, so tensile load, meaning this is under tensile stress. So we can just use the equation for tensile stress, which is just axial stress, P over A. We're given the allowable stress, which is 120 MPa. So 120 equals P over. Now the question here is, what is A? A is a cross-section of your tube. Hollow tube, so at the center, there's nothing there. Therefore, this is the only area carrying your load, which is a ring. And recall, area of a ring is just pi over 4 outer diameter squared minus inner diameter squared. And that inner diameter is 100. Okay? That's our equation. Now let's double check if our units are uniform. MPa, Newton per millimeter squared, our diameter is in millimeters squared. So uniform units, no need to convert. And then from this, you can solve for, P rather, sorry. P is 400 kilonewton. So there's a problem there. It's in kilonewton. My stress is in Newton. So you have to convert that. Again, kilonewton to Newton is just multiplying by 1000 or 10 raised to 3. Okay, now that we have that, please solve what's D sub O. Correct, Marino. Who else? Christian, correct as well. Denaga. It's 119.35. And then this is in millimeters. And that's our answer. And that's why I drew this so that I can figure out what the area is. Okay, that's 5. Now let's have the last question. Question number 6. Okay. So question number 6. A homogeneous 800 kilogram bar, AD, is supported at either end by a cable as shown. So you have your bar, cables. Calculate the smallest area of each cable if the stress is not to exceed 90 MPa in bronze and 120 MPa in steel. Okay, so we're basically looking for area. Now we have this term homogeneous. Why is that important? It's important because that means the weight of your object will lie on its centroid. Okay, so we have a bar here, so immediately weight is at the midspan. If it's not homogeneous, your weight can be applied anywhere depending on the composition of your bar. Okay, so that's why it's included there. It's homogeneous so that we know, oh, it's just going to be at the centroid. Okay, so keep that in mind. And now let's try to write our given. So mass of your bar, 800 kilogram. Then stress in bronze, 90, in steel, 120. Okay. So that's our given so far. There. Now, once again, solve for dimension is the same as solving for force, wherein, or rather solving for stress, wherein we have to get its internal force first. Okay, so let's solve for internal forces at your bronze and steel cables. To do that, let's start with a free body diagram. Okay, so we have your bar here, right? These are cables, therefore, again, they're only carrying tensile loads. So it's going to be away from your object. Let's call that PBR or FBR. PBR. For tensile load in your bronze. And then here, steel, again, away from your object. So PST for internal load on steel. And then this has mass. Mass is given, so you have to include that. And with mass comes weight. So weight is just mass times gravity. So that's 800 times 9.81. Okay. And then to solve for PBR or PST, you can just use summation of moment at either A and B. If you use summation of moment at B, you'll solve for PBR, and then afterwards you do summation of forces Y equals 0 to solve for PST. You can do that. Okay, that's allowed. But I'll show you the faster way. And the faster way is by using symmetry. So to know if an object is symmetrical, get its center line. if the left equals the right side or looks like the right side in terms of placement, then it's symmetrical. Okay? Now, for example, if there's another load here, like 10, it's not symmetrical anymore. But if we put another load here that's 10, that's also equidistant from the center, then it's symmetrical. Okay, so that's how to test symmetricality, or symmetry rather. Okay, so correct, it is symmetrical. This is 10 meters, so this is 5, 5. Your reactions are equidistant from the center. To solve by symmetry, that means PBR is the same as PSP. Okay, left equals right. And those two reactions carry your load evenly. So that means you're just going to take the total load divided by 2. The only load we have, though, is the weight. So 800 times 9.81 over 2. Once again, if you have symmetrical loads here, let's say 10, 10, then include that here, plus 10, plus 10. Okay? All right, please solve what's P. Correct. Correct, Almira, and who else? Who else? Christian. Three ka na eh. Chloe. Chloe, correct. And then verse. Okay, correct. The answer is 3,924. And then from this, that's Newton, we can solve for dimension. So using these equations, stress equals force over area, PBR over ABR. There. So stress VR is 90. PBR is 3924 over ABR. Now let's check if our units are uniform. 90 MPa, Newton per millimeter, this is Newton, so uniform. From this, please solve what's ABR. Correct, Jan? And Raymond. Baldo, Wico. It's 43.6 millimeter squared, right? Because Newton per millimeter, so the resulting unit is millimeter squared since it's area. And then let's do the same for steel. Sigma ST equals PSP over area ST. Sigma ST given 120, PSP 3924 over ASP. Please solve what's area. Correct. Mariano and Eric. Sacro. Ablao, and also Matthew. So 32.7. Hey, by the way, if you're wondering why is this Newton, because this is mass times gravity, that's kilogram times meter per second squared for your gravity. Kilogram meter per second squared is Newton. That's why this is Newton, okay? And then our resulting answers are this. Now, let's read the question again. Smallest area of each cable. That means our final answer is both. Okay? Now, if the question is, what is the allowable diameter of the cables? Okay, there's no mention of each. Then you should use 43.6. So minimum area, cross-sectional area of cable is 43.6. Okay? So it's opposite with your force. we're looking for maximum force, you take the smallest value. If you're looking for minimum area, minimum dimension, you get the highest value. Why? To explain, look here. This means that your steel needs at least 32.7 millimeters squared area for it to function. Anything less than this, your steel will fail, your cable will fail. Same thing here. Bronze needs at least 43.6 millimeters squared of area in order to function. Anything less than that, bronze will fail. Okay, so that's why I can't use for 32.7. That's less than 43.6. If I use this, bronze will fail. That's why whenever looking for minimum dimension, I use the maximum value. Okay, but again, for this problem, it's not asking that. It's asking for each cable. So your answer is both. And that's it for numbers 5 and 6. Do you have any questions? Please answer in the chat. Okay, no questions. Great. That ends our topic for axial stress. Now on Thursday, we're going to start with a new topic, which is your shear stress. And then on Saturday, you will have your seat work number 1. Coverage is axial stress. Okay. So that's it. A few reminders before you go. For those who haven't answered the diagnostic exam, you have until Saturday to answer it. Again, you can just answer it whenever you want. You don't have to message me about it. And then for those who haven't watched the orientation video, please do so. It's located under Zoom recordings in your Blackboard tab. So let me show you. So please watch this. Okay, and then you can also read this orientation. And all of our classes are recorded and uploaded, and I'll give you the link here. So these are all the activities. And you'll even see all the activities for each week here. Okay, so there. So as you can see, for week 1, we had your diagnostic exam. For week 2, we'll have your classwork. So these are the activities for each week. Okay? So for those who haven't, please read and please watch this orientation video because it might answer any question you already have. Before you message me, please read and watch this first. Okay? So do you have any concerns, clarifications? No more? All right. Once again, lecture Thursday, seat work Saturday, diagnostic exam deadline Saturday. Please read, watch orientation video. And since you don't have any more questions, I'll see you on Thursday. You may go. Goodbye, class.
Thank you, ma'am.
Thank you, ma'am.
Thank you po.
You're welcome.